Hello everyone. In this talk I will describe my work along with Fredrik Johansson on data-dependent priors for domain adaptation bounds. We have looked at this in the context of neural networks, as in most realistic settings, those are the ones that are used. They have been proven to be quite successful in all manner of different situations. However, they are non-interpretable by nature, which is not always what we would like. And they've also been known to fail when transferred to new settings from the ones that they were trained on. An example of this would be in healthcare, when we have two data sets of chest x-rays that were taken from two different hospitals. So from these two hospitals, we would have a source domain and a target domain. So the source domain being where we train our classifier on, and the target where we would hope to actually deploy the model after training on one hospital. So the task would be to identify a lung disease, let's say, and we would have somewhere around 25% error on the source, but when we then deploy to the target, we would have something like 40% or more error, which would be quite the degradation of performance. And this is not uncommon, especially not in this setting, but also in others. So we would like some guarantees for how well we do perform on any given target domain. So we would then want something like the error on the target to be related to the error on the source by some function or some terms. But since we can't actually get at these distributions in general, we'll have to make do with the difference between the target error and the empirical source error in general. And for the bounds that we have looked at without using the technique that we're going to talk about with data-dependent priors, we find that both the additive and multiplicative type bounds that we've looked at both fail to be anywhere near informative. So we see down here the blue is all the target errors. We can ignore this one, but the bound themselves are quite different in size, and this is the best that we were able to get. So not very good. But additive and multiplicative is not really standard nomenclature, so we'll be more specific. So we can take these generalization bounds, which are generally functions of domain shift in the case of domain adaptation, but also of sample generalization error. So we can further decompose this into what we call additive and multiplicative type bounds. So this would just be, as it says here, when the sample generalization and the domain shift terms are either added to each other with no common interference, or when they are actually multiplied, which are two distinct possibilities. So if we just look at this classical standard learning theory, we get something like this, like the bound from Ben David et al., where we have the target error is bounded by the source error for some classifier plus some sample generalization term, and also some associated domain shift terms here. In the sample generalization terms, we have the dependence on this D parameter, which is the VC dimension of the classifier space. This is sort of a measure of complexity or of the expressiveness of the classifiers that inhabit the space. And for neural networks, this is quite large and quite big number in general, especially for the realistic type of networks that we consider, that we use today. And this is not really so useful. So what we mean then is that neural networks are complex classifiers. That much is quite obvious. They have a lot of parameters. They can express all manner of different functions, which is a good thing in some respects, but poor in this specific circumstance, because the metrics of complexity depend on this number of parameters or layers in a sense. For an example, the VC dimension has shown to be, in best worst case, so to speak, linear in the amount of parameters and linear in the amount of layers. And since we have millions or even billions of parameters in the newest hottest neural networks of the day, well, this doesn't bode well to have tight bounds on performance. So we will need a huge amount of data to mitigate it, which in many of these settings is not really feasible. So why is this? Well, it is more or less due to how we look at it in statistical learning theory. In the PAC framework, as it's called, we look at it like this. Consider this square here to be the entire space of classifiers. And these two dots here, H and H prime, to be two just generally different classifiers we just picked from the space. The advantage of the standard statistical learning theory is that these bounds will hold for all classifiers in this space. No matter which one I pick, it will always hold. And therefore, it will always hold even for the worst type of classifiers, which in the neural network case can be arbitrarily bad. You can find an arbitrarily bad neural network that will always be wrong on all your samples. So we need something different. That is where the PAC-based framework comes in. It's a similar type of framework, but it's based on Bayesian inference in a sense. So we have prior and posterior distributions which we relate to each other. So we start with our prior P, and then we add our data to our classifier and let it train and become informed, and thereby we get the posterior Q. So in this framework, we have these two quantities, one of which is data dependent, that is the posterior, while the prior is freely chosen, and the shape of these two are also freely chosen by the experiment designer. So what we can do here is that maybe think that could we influence this in some other way, add more information about how we get this prior to be closer to Q. So, but why would we want that? Is a reasonable question to ask. Well, in the differences between these two frameworks is that for one, the bounds hold uniformly, but for the others, they hold an expectation overdraws from this posterior. So we have a data-dependent measure here. Then the same is true for the complexity measures, which in the PAC or standard statistical learning theory case are generally quite worst case ideas that will hold for everything. While in the PAC-based case, you're just constrained to these two distributions, the prior and the posterior, which is related to something like the KL divergence or something like that. Which means that if you can get the prior and the posterior to be close to each other, this will then become quite small, which is exactly what we would like to do here. So an example of a PAC-based bound is this from McAllister, where it's a supervised learning bound, but it's similar as all the others. We have something we want to estimate, which we estimate with the empirical source risk plus some sample complexity term. You can easily add a domain shift term to make this into a domain adaptation bound. So again, the prior will affect this complexity term, or KL term in this case. Increasing it, the further away the prior will be from our posterior. So we would like to influence the pick of the prior to be closer. Quite a simple idea, but it's quite effective, as we will see. So how we do this is we'll break it into two parts, essentially. We will start to learn how to pick a good prior, and then we will perform the actual learning task and then evaluate the performance bound after that. So we achieve that by using this algorithm, which is by the work of Jagaite et al. Recently, which, as I said, you take a portion of your data as alpha, and you learn your prior from that. So you use data and train a classifier to be better, and therefore understand, oh, that's the prior I want, somewhere around this. So you train up until some point, you take those weights, make some distribution around those, and then you continue training with all of your data to get the posterior distribution. Thereafter, you take away the data you used to calculate or inform yourself about the prior, and then you evaluate your bound. So in this, there is an inherent trade-off that you can choose how much data you use for the prior and how much you use for the bound, respectively, which is quite a non-trivial question. So p hat will then be something like this, where we start over here by some random guess, and then we use SGD in this example and sort of search our way through the space and find some better classifier that will in general be closer to Q. This will not be, of course, in a straight line. We don't know exactly where Q is. We're not using any deterministic optimization functions. We're using standard stochastic gradient descent. But in general, the intuition is that we will get closer. And throughout, we've always made these assumptions of covariate shift and overlap, which are quite common in domain adaptation. Covariate shift just being the conditional distribution of labels given data, being the same across source and target domains, and overlap being if we can see the data in the source and the target, you will see it in the source. Both quite common and quite strong assumptions, but we will need them to be able to evaluate the bounds at all. To understand the bounds that we're looking at in the pack-based framework, we're going to need to introduce two quantities here, the expected joint error and expected disagreement, ED and DD, as I've written them here. So the first here is the expected joint error, which is how often two classifiers drawn from the distribution, posterior distribution Q, make the same errors. I've written the row here, but it's Q. So how often do they make the same mistakes? Disagreement, quite naturally, is how often do two drawn classifiers disagree on the labeling of the same data point. And empirical variants of these are just replacing expectations with sample averages. So the first bound that I'm going to show is a simplified version of a bound from Germain et al., where we have, as we see here, the target error and expectation, which is bounded by some beta term plus this decomposition of joint error on source and disagreement on target, which one could liken to more or less the empirical risk in this case. In addition to that, we also have the same term multiplied with the whole of the sample generalization term that depends on the KL here. And this beta term is one of the domain shift terms in this bound. So it's more or less an importance weight. As you can see, it's very clear, closely related to it. But there's also another term that which we don't report here that is 0 because of our assumption of overlap. In the additive case, we have this bound by the more or less the same authors, which is on a more similar form to what we showed in the pack case with empirical risk, sample generalization, and domain shift terms, plus some extras. These are just constructions of the two quantities that we showed before. However, you should note that this lambda q here is not really observable without target labels. So unless you have that, you cannot actually estimate what this is. You're just resigned to assuming that it's small and moving on. So we will keep this in mind when we look at the results. One of the learning tasks that we've tested this on is this MNIST-M mix, where we have taken a few examples from MNIST-M with the label 0, mixed it with a lot of examples from MNIST with the label 0, and just continuously shifted the amounts until we get to the label 9, where we have a majority of MNIST-M 9s, but a few MNIST 9s. So this means that we have a known value of the beta term that we showed before in the multiplicative bound. It will be about 11, which is quite harsh, which will make these terms very influential very fast. But how would we ever estimate this otherwise? We have to assume that it might be bad sometimes as well. And the target, this would be how the source is distributed, while the target would be just the complement here. So the slope, so to speak, would go the other way. And results here from our experiments is showing that for the multiplicative and the additive bounds, we both get a tightening effect. We are within the informative area, at least, and the additive bound itself is actually quite tight in the beginning. However, as training goes on, the KL term will increase as our posterior will move away from our prior. Therefore, we see this increase as we go away. And here we have taken about 30% of the initial sample and informed our prior with that. Our preliminary results also from an X-ray task, which we've just mixed two X-ray data sets, more or less with slightly different proportions. Well, in here we have a kinder beta term of about 4. However, we see that it's still not enough to tighten it all the way down close to where the target error is. We're quite a ways off still, but also we're still in the informative region at least. So this can be a step on the way to getting tighter generalization bounds, which is sort of what we wanted to show with this work. So again, if we look at the MNIST case, we've seen an obvious tightening of the bounds from what we saw in the beginning, much closer to the actual target error here, which is useful. We also looked at how the different parts of the bounds vary over training time and how large of an amount of the final bound they are. And we see here that in the beginning here with data-dependent use, we can see that the prior makes it so that the training error more or less takes up all of the bound, but rapidly drops off as the KL term increases as training goes on. We see also that the disagreement term in the multiplicative bound does not factor in very much. We see sort of a very similar image for the additive bound. This is both for the X-ray task that we preliminarily evaluated. We see here then also that the source error initially is quite a large part of the bound, along with the domain shift terms here. Also to note that the unobservable lambda q is still a large part here in red. But as time goes on, the posterior moves away from the prior and the KL term starts to dominate, which is the case without using data-dependent priors. Then the KL dominates fully all the time. So, conclusion from this work is that regular bounds that have been proposed are generally uninformative, i.e. they don't give us any indication of how well we're going to do outside of our assumed source domain. They can also be hard or even impossible to calculate in practice, and we find that this new notion of using data-dependent priors can be useful in tightening these existing bounds. However, this technique alone is likely insufficient for actually achieving tight informative bounds in practice in the realistic settings which we aim for. So more work needs to be done. Future directions to study is to investigate the possibility of optimizing the posterior to be closer to the prior. We would need some sort of regularization or similar, but also investigating if we can introduce data dependency in the domain shift terms. That is to say, we could use data to actually estimate the domain shift as well. And that's it for me. Thank you for listening.